Hey, this is Steven, and welcome back to my DIY Dyno tutorial. So let's continue on. So I found I found a page here where it's talking about dry rubber and dry steel, and the coefficient of friction here, and you can see it's basically the last page. MU. Dynamic coefficient of friction and restitution. Dynamic and so basically, mu is the symbol, so they actually spelt it out as mu. Interesting. Let me show you. Friction coefficient symbol. Yeah, so yeah, this thing here. Friction is usually symbolized by the Greek letter mu. So I was confused there. Okay. So we want to look at static. So dynamic means that the two materials are slipping across each other. We don't want that to happen. We want them to stay sticking. And when we say that, basically it means that these two materials are spinning at the same speed, right? Once they slip, then they go into dynamic friction, and that means that one material is actually going faster than the other material. In this case, the tire is spinning faster than the roller because now we don't have enough friction to keep that down. So that is one of the issues. So we do see this now. We see dry rubber, dry steel. Anything else? No, dry rubber, dry steel. Okay, so friction co. I'm going to say equals, and then here's where you're going to see where I enter in the value here. So we want static. Static is 0.8. 0.80. Oops. And then we're going to go here, and then basically what I hit is I hit the quotation marks. So here's the lower, the smaller, the non-shift one. So it's to the left of the enter symbol on your keyboard. And when we do that, it enters in the unit entry place. So friction is the force that you could put against friction. So friction is a force that is counteracting the direction of movement. So if you put your hand on the table and you move your hand across the table, the friction is going against your movement. Remember what I said in the last video where I said that the world restricts, wants stuff not to move. So what it does is it has a whole bunch of these things like air resistance and friction and stuff to try to prevent that from happening. So friction is a force that counteracts the movement of, or the potential movement of a material. So, for example, static friction is if I put my hand on the table and I push it down really, really hard, it has not moved yet, and once it moves, then that's dynamic. So, it's a what's the word I'm looking for? It has two things that have to do with the force. One is the friction coefficient, which we know is either the static or dynamic. In this case, static, 0.8. Then it's the normal force. Normal force is basically, so I'm pressing down on my table. Now, one of Newton's laws, there are multiple, but one is that if you're pushing against something and it's not moving, that must mean that it is pressing back towards you with the same force. So if I press the table, the table's not moving, right? So that must mean that I'm pushing on the table and the table's pushing back with the same force where nothing's happening. Everything is staying static, there is no motion. Now if I have this bottle of isopropyl rubbing alcohol here and I put a force and I push it across the table, and the bottle is now moving, that means that I'm applying a force, but the bottle is not applying a force the same way back. But if I a force is mass times acceleration. So let's say that this bottle is not accelerating, it's moving at a constant speed. Then that means, if it's moving at a constant speed, that means I'm applying a force the same as the friction force that is counteracting it. Anyways, that was a little bit of a tangent there, but a little pretty interesting. So friction force is the normal force, which is basically, in this case, we're talking static. So we're not talking about if you're like sliding down a building or something. The two pieces are static. The roller is pressing up on the wheel, and the wheels are not they're not translating in space. They're just rotating. So that means that the weight on that wheel is equal to the normal force, because nothing is moving, translating in XYZ space. It's only rotating. That must mean that the roller is pressing back up against the wheel at using the same force, which is the normal force. Because if it wasn't, that means that the car is now going to fall off of something. It's going to, the roller's falling off or something, or the roller has spun off or done something, and you're going to cause some damage. So we're going to assume that those two are still well meshed. So the normal force is going to be equal to the weight of that weight that's on that tire. So friction is equal to that divided by the normal force, which 1 over pound force. Well, let me do 1 over. What I could do is I could do pound force 1 divided by 0.80. Oops. And there you go. So now that's what friction coefficient, and if I type it again, it should fix it. Yeah, there you go. So wait a second. Friction coefficient. Actually, it's non-unit. It's non-unit. No units. So it's unitless. Because basically we're taking this because the normal force is a force and the force of friction is a force. So that's why they call it a coefficient. A coefficient is generally unitless. So yeah, it's unitless. Friction is unitless. Not the force of the friction, but the coefficient mu. Mu is unitless. That's why you don't see any units here, right? Sorry, my bad. Okay, normal force. So this is where we should put a slider. So let's say normal force, which is basically the force on that particular tire on that particular corner. So in this case, and also it's divided by, no. I'd have to do it, but I think it's pretty much divided by 2 because we have 2 rollers. So this is going to be whatever divide by 2. So I'm going to say divided by 2, and basically what this is this is in pound force, and this is the weight of the car. So let's say up to 5,000 pounds. Minimum value is 100 pounds. Step size is every 100 pounds. So this is the per tire. So on my car, the curb weight of the car, including yourself, so you could add yourself in there. I'm just going to round myself up to 200 pounds. I'm 160, but because I'm doing 100 pounds, I'm just going to increase myself to 200 pounds. So the Mustang, I think, is like 2,300 pound curb weight, and the Rabbit is 1,800 pound curb weight. So let's say here I already have the Rabbit loaded up. So let's say the Rabbit is 1,800 pounds, not including gas. and plus the gas is in the back anyways. So we're talking, and we're going to say that the car is level. In actuality, it's probably not going to be level. It's probably going to be that these tires are up and the other tires are back down, or that the back tires are higher than the front tires, so we're putting more force on the front tires, so we have more friction. So we have 100 pound force. Sorry, that's there. So 1,800 pounds plus myself, that's 2,000 pounds. So 2,000 pounds divided by 4 is 500 pounds. And then so 250 pounds per roller. So this is 250 pounds. Right, so let's just say 200 pounds. Let's do 50 pounds here. So let's just say 250 pounds. And again, we have to do this moment, not the moment dual roller, but the regular moment then, if that was the case. Okay, so that's normal force. So max friction force is equal to normal force divided by 2 times friction co. Friction co, max friction force is 900 newtons, pound force. Pound force. Okay, so this times 80, this times 80% of this is 200 pounds. Okay, so what that means now is we get to use this equation from the last one. So torque is equal to I alpha plus omega. So the maximum amount of torque, so max torque is force times distance, right? So this means that on the top of the roller, we can only put down 200 pounds of force at the very edge of the roller. Now, max torque is the way to think of it is it's just like when you're turning a bolt. It is the amount of force you put at the end of the wrench and how long the wrench is. So in this case, it's the radius, right? So we want the OD, and it's on the outside of the wheel, the outside of the drum. So it's OD divided by 2, because we want the radius, times max torque is force times distance times the max friction. Okay? But technically, it's actually not the torque. It's not this torque. It's the torque of the wheel of the car. So not the torque of the drum. So we need to change this. So basically, we need to know how big is the rim. Now, this is going to come into effect of this, what does this number mean? So I have on the rabbit, so this is, I'm going to do a calculator here, rim size, and this is going to be, generally they're in inches, rim size in inches, and this is 1, and maximum I'm going to say is like 30, right? So rim size, I believe they are 14s on the Rabbit and the Mustang. Then we have the next one is going to be tire thickness. Tire thickness. So tire thickness is, and then this is going to be in millimeters, and this guy, SwiftCalcs, will change that for me. So here we see that this is 45. So the 2-digit number that actually follows the tires section tells us the aspect ratio of tire profile measurement. In this example, the 45 indicates that the sidewall distance from the wheel rim to the outside of the tread is 45% of the section width. So basically it's 225 times this percentage. While a tire with a want to look more like a donut because we know that the tire size shown in this example has a section width of 8.86 inches. The aspect ratio is 45. I believe that's this 225. 225 to millimeters to inches is 8.86 inches. And 45, so here times 0.45. So this is going to be unitless there. And so this is going to be, I'm going to say, I'm I'm gonna call this torque radius. Radius. Okay, so I think I have 50s on the Mustang and the Rabbit. So, but then it matters tire. So radius. So let's keep that there, and let's indent this, and let's put in a slider here, and then we need a tire width. And now this is going to be in millimeters. So this is in millimeters. Millimeters. And maximum is, let's say, 350 or something. Minimum, obviously, is going to be like 100, I guess. Okay. So let's say I'm running like 205 or something on the Rabbit. So 205, that's fine. Torque radius is equal to tire width times tire thickness, and then this is going to be divided by 100. 100. Oops. So tire width times tire thickness. Let's go ahead and put that all in one. And then that's just the top, and then that's going to be plus rim size divided by 2. And torque radius. Oops. Okay. Change unit to inches. Oops. Not inches of water. That's volume. I mean, yeah, vacuum. Okay, so so not this. So this is now equal to torque radius times max friction force is max torque joules, and we're going to do inch, or in this case, let's say foot pounds. Oops. What the heck? Foot force. Foot. Times pound force. There. So joules is energy. So it's also similar, the same unit as torque. Okay. So 4 pounds, 183 foot-pounds. Okay. Now we need to know, that's the max torque, which is basically, so basically what this is the distance from the center that you're driving with the engine, the center of the tire, to the end of the tire, and the friction that you could put this way along this tire, right? So now what that means is I could put down 183 foot-pounds of torque. Now, what I'm going to do here is, let me see, can I move this? I don't know. Oh, yeah. Okay. So, let's do that. And then basically, so 183 foot-pounds is the max torque at any RPM. So let's say here measured RPM, and then let's have max horsepower is equal to measured RPM times max torque. Max horsepower. I think, let's see, it should do the conversion. Yep, it does. So this is watts, which is the, oops. What the heck? This is watts, which is a metric way of measuring power, but we're going to look at imperial, which is horsepower. Horsepower, so that's 19 horsepower. Oh, at foot-pounds. Okay. But I think the max foot-pounds is at like 5 something. 28 horsepower. No, that's not right. let's see, 1979 Rabbit, or 1.6, I think it's like a 1984. Mark 1 Rabbit Wikipedia. Okay, so here we go. Alright, let's look here. They have a big chart. There it is. So here's the 1.6 liter, or is it diesel? Here it is. 1.6 liter diesel. 72 foot-pounds at 2,300 RPM. Measure RPM. So basically what this is this would be the horsepower at that RPM. So that's not necessarily, well, I guess you could say that that's the max horsepower that you could be pushing at that point. So let's see here. Diesel. Okay, so diesel, we're talking only 72 foot-pounds, right? So 72 foot-pounds. So let's see here. 72 foot-pounds at 2,300 RPM, 53.6 horsepower. And then the turbo diesel is 70 horsepower and 96 foot-pounds at 2,600. So, but what about a 1965 Mustang Pedia? Or not 65 Mustang, but Mustang. Let's see, does it have a big chart? Does it have a big chart? It should have a big chart. Here we 1965 Mustang 289 torque and horsepower rating. Okay, so this is an A code. I have a C code. C code is a 2-barrel carb, so it's a little bit lower. Okay. 4-barrel manifold and carb. Well, that's not very helpful. I've already been there. Been there, done that. Okay. Okay, so let's just use this one. So here, maximum horsepower, 225 brake horsepower. That's at the engine. Is it decode? Never heard decode. Oh, okay, code, yeah, decode. Never heard decode. Very strange. But it has lower horsepower. Okay, so let's say 289 C code. This torque. Okay. C code. Control F, C code. Oh, here we go. Here we go. Compression ratio. Mine's way higher than that. I think it's at 11 or something now. Engine torques. Oh, torque spec. That's for a different deal. Okay, here we go. Torque C code. Oh, right below the A code. Interesting. K code. Okay, so C code is the lowest for 289 V8. 282 torque at 2,400. So we have a issue here. 183 foot-pounds before slipping is the max amount that we could dump, right? So what can we do to change that, to make that better? Let's see. What the heck? Anyways, what can we do to make that better? We can increase tire size, basically. Right? We could increase tire size to make the tire bigger, or we could decrease it down to one roller, and then we have all that on top of one roller. And then we could increase the friction there because we're increasing normal force. Or we could put more than a quarter of the weight of the car on that. So what I'm saying is that we could stick it. I could put these on the driveway, so that now the car is kind of perched down onto the rollers, and now we have 50%. Now we have like 75% of the car's weight pressing on it. So let's see that. So obviously we could change here. So let's say we have 75% of the weight pressing on that, 2,000 pounds. Oh, but here's the deal. This will work for the Rabbit, but the Rabbit is different than the Mustang as far as curb weight. Let's see if it's good. Curb weight. Transformation. A 1965 Mustang curb weight. 1965 curb weight. Total hardtop weight approximately 2,600 pounds. Weight. Okay, so 1965 Mustang, the hardtop, the convertible, the fastback, all three bodies were blah blah blah, certain track width, total wheelbase, blah blah blah. The hardtop weighed approximately 2,500 pounds. So let's say 2,700 pounds. So this will work for the Rabbit. So let's say now we're doing 2,700 pounds, and that divided by 4. Oops. 2,700 pounds divided by 4. So this is even ground, and then divided by 2. It's 337 pounds. So let's make this a lot smaller. Let's say that this is divided by 4 most likely. So if that's the case, and it's 5,000 pounds, so let's say it's 1,200 pounds, let's say. Or let's just say that this is 1,000 pounds. And let's say that this is every 10 pounds in this case. So let's say that we're at 14 pounds. 340 pounds. 340 pounds. So max is 250 foot-pounds, which is still too low compared to this guy. Now, remember, what one of the things that I want to do to these rollers before they are installed is I want to knurl them. Now, knurl is basically, let me see if I can show you. Knurling pattern. Images. Okay, so this is basically what a knurling pattern looks like. And basically, it's these diamond shape. You'll see it on a lot of like flashlights, or if you go to the gym, you'll see them on dumbbells. You'll see them on barbells. You'll see them on pull-up bars. You'll see them on I don't know. I don't know why they don't have them on baseball bats. They should probably have them. I just, for whatever reason, was thinking baseball bats. What do I have around here? Bike handlebars. Scooter handlebars, pretty much anything that you grab onto. It increases your friction because basically when you press your hand against it, your skin goes into these little bottoms of the diamonds, and it increases the friction there. It increases the contact area of your skin against the material, and also it basically acts as a wall. So like the tips of the diamonds acts as a wall and kind of pushes back against your hand. So this will increase the friction of the roller. So I'm thinking that this is going to work for the Mustang. Now, obviously, we could increase the amount of force. And anyways, this is assuming that it's 50-50, when in this case, well, this is a rear-wheel drive car, so technically a lot of the weight is back on the engine. So we could put it to where it's pivoting inside the garage, and I have it out on the driveway, and it is pivoting down onto this thing. So let's say again, let's say that 75% of it is onto. Let's say I have it perched right up on the garage, and 75% of it is down on these tires. Let's say. So 75% of 2700.75 times 2700 is 2025 divided by 4, and then again divided by 4 again. Sorry. Divided by 4 and then divided by 2, 506.25. And then divided by 2. 253. So this now, wait a second. Oh, so this one, sorry, this number is divided by 2, because it's all of that weight is on the front 2 wheels, so we divide that by 2. 2025 divided by 2 on 2 wheels, and then divided by, this is on 1 wheel, and we divide it by the rollers, so this is 500 pounds. So 506 pounds, 510, let's say. 510 pounds, and we're talking 373 foot-pounds of torque max, which is plenty enough for what we are trying to do here. Obviously, my engine on the Mustang is not stock, and the engine on the Rabbit is not planning on being stock either. So the numbers are going to be quite a bit different. For this one, I have for my Mustang, I have flat top pistons, so the compression is a little bit higher. I have tri-Y headers, Flowmaster exhaust. I have a slight cam. I have high performance air filter, etc. So it's probably for brake horsepower, it's probably up. It's got some K-code equipment on it, so but not. It doesn't have a 4-barrel, so I'm gonna say it's probably in the 240 range or something. 240, 250, something like that. Brake horsepower. I believe this is brake horsepower. So what it's actually putting down to the wheels, I'm not exactly sure. And then again, this is torque at the engine, I believe, so not at the wheel. So again, you have loss through the transmission and the transaxle and the differential and the bearings, etc. So, yeah. I think that we are good to go on this. Now, we can do the friction. Now, the next thing that we need to find out is how long is this dyno run going to last? And also, if we could find bearings that can support half of this. So this, basically, 408 pounds, right? Or more. So let's say I want to do a truck that's 3,000 pounds, 4,000 pounds. So, but if that was the case, the truck is probably not going to scale as much with the horsepower. So we can kind of go backwards, and where we put the back, or we put whatever is heaviest of the truck, or whatever we're putting on there, out of the garage. And we could kind of pivot the garage and use it to our advantage to kind of distribute. Because my driveway's on a hill, so we could have the garage is flat with respect to the horizon, so that be flat, and then whatever we need to either add weight or subtract weight off sit out on the driveway. So either we could have the back side of the truck be out on the driveway and the front side be on the and the front side be on the, well, it depends on if it's front wheel drive or rear wheel drive truck. Most likely it's a rear wheel drive truck. So we put the rear wheels on the rollers, and we put the front side out inside the driveway. So now we have less force down on it, and that all is determined around the horsepower that I predict it to be. But it looks like here we'll be able to handle pretty much anything up to for this weight, for something that's 2,700 pounds, we could probably take anything that's under 400 foot-pounds of torque, which is pretty big. All right, thank you guys so much for watching. I'm going to try to finish up the water jet videos this week here, so I could be waiting for those parts, and then we could do this. And when I kind of don't feel like doing this again is the dyno is going to kind of be a side project. The next, the water jet, again, the water jet, the DIY metal mill, the CO2 laser are my main projects. Those three. All right, thank you guys so much for watching, and I will see you guys in the next video. Take it easy. Peace.